You feel still. You are not. Right now, as you sit there, our entire galaxy is moving at roughly 1.3 million miles per hour, about 2.1 million kilometers per hour through space. Not rotating, not expanding, moving. At that speed, you could travel from Earth to the Moon in under 4 hours. But this isn't a spacecraft. This is the Milky Way. 100 billion stars, dark matter, gas, dust, you, all sliding through the universe together. And the strangest part? We don't feel it. No wind, no vibration, no sense of direction. Just a quiet night sky that looks calm and fixed. But that calm sky is lying to you, because the universe has a reference frame. And when we measure ourselves against it, something doesn't add up. Look at a full sky map of the cosmic microwave background. It's the oldest light we can see, the afterglow of the Big Bang, released about 380,000 years after everything began. It fills the entire sky almost perfectly evenly. Almost. When we measure its temperature carefully, we see a pattern. One side of the sky is slightly warmer, the opposite side is slightly cooler. This is called the CMB dipole, and it's not random. It means we are moving. If you move toward light, it blue shifts. If you move away, it red shifts. The same thing happens with this ancient radiation. One side of the sky is compressed by our motion, the other is stretched. The imbalance is tiny, but the implication is massive. The Milky Way has a peculiar velocity. That's the term, peculiar velocity. It means motion that cannot be explained by the expansion of the universe alone. Because yes, the universe is expanding. That's called the Hubble flow. Galaxies drift apart as space itself stretches. But peculiar velocity is different. It's motion on top of expansion, a directional drift, a push or a pull, and ours is strong. The arrow of that motion points in a very specific direction in the sky, toward the constellations, Centaurus and Norma. So we ask the obvious question, what's over there? At first, the answer seemed simple. Maybe just a cluster of galaxies, maybe several. Gravity pulls. That's what mass does. But when astronomers began mapping galaxy motions in our local universe, they saw something else. Galaxies weren't just drifting randomly. They were flowing. Imagine leaves on a river. Each leaf moves on its own. But step back, and you see the current, a direction, a convergence point. That's what we saw on cosmic scales. Thousands of galaxies, including ours, sharing a similar vector, a large-scale streaming motion across hundreds of millions of light years. This is called a velocity field, and our velocity field has structure. It bends, it narrows, it funnels, like water finding a basin. So again we asked, what's in that direction? Here's where the story tightens. When we turn our optical telescopes towards Centaurus and Norma, we don't see much. A band of stars, thick dust, a bright strip cutting across the sky. That strip is our own galaxy. The Milky Way is a flat disk about 100,000 light-years across. We live inside it. So when we look along its plane, we are staring through dense clouds of gas and dust. That dust blocks visible light like fog blocks headlights. Astronomers call this region the zone of avoidance. About 20% of the sky is partially hidden behind it, the one direction our galaxy is moving toward. That's not poetic, that's measured. The vector of our peculiar velocity points almost directly into the zone of avoidance, the one region we couldn't see clearly for most of human history. So we had motion, we had direction, but we didn't have visibility. It's like watching trees bend in the wind while standing inside a forest. You know something is pushing them, you just can't see what. That tension sat unresolved for decades. Then came radio astronomy. Radio waves pass through dust far better than visible light. So astronomers began scanning the hidden sky using the 2-1 centimeter hydrogen line. Neutral hydrogen gas naturally emits radiation at this wavelength, and galaxies are full of hydrogen. Suddenly, faint signals appeared behind the Milky Way's glare. Hidden galaxies. Not a few, hundreds, then thousands. The darkness wasn't empty, it was crowded. But here's the detail that changed everything. When researchers measured the redshifts of those galaxies, their velocities relative to us, they weren't scattered randomly. They were clustering, and more importantly, their motions were coordinated. They were falling in the same general direction we were, toward something deeper inside the zone of avoidance. We thought the expansion of the universe explained large-scale motion, but the CMB dipole said we had extra velocity. We thought maybe it was a local cluster tugging at us, but the velocity field showed a flow much larger than one cluster could produce, and the direction of that flow disappeared into the one part of the sky we couldn't see clearly. That's when astronomers gave it a name, the Great Attractor. Not a planet, not a black hole, not a single object, a gravitational influence, a region of space with enough mass to bend the motion of our entire local group of galaxies, including Andromeda, including Virgo, including us. And at this point in the story, we still didn't know what it was. We only knew it existed because of how everything moved. Think about that. We detected something massive, not by seeing it, but by watching how the universe around us reacted, like deducing a submarine from the waves it leaves behind. The Great Attractor wasn't a discovery of light, it was a discovery of motion, and the motion was undeniable. When we subtract the expansion of the universe from galaxy velocities in our region, what remains is a coherent flow of hundreds of galaxies streaming toward a common gravitational basin. That basin sits roughly 150 to 250 million light-years away, close in cosmic terms, far beyond intuition. The light from that region began its journey before the first dinosaurs walked Earth, and yet its gravity influences us now. You are sitting on a planet orbiting a star inside a galaxy that is falling towards something you cannot see with your eyes. We are already moving, but here is the part that should unsettle you. Even after we mapped the hidden galaxies behind the Milky Way, even after we identified massive clusters in that direction, the numbers still didn't quite add up. The gravitational pull required to produce our measured peculiar velocity seemed larger than any single visible structure could explain, which means one of two things is true. Either we still haven't seen all of it, or the Great Attractor is not one thing at all, and both possibilities lead us deeper into the blind spot. Because the arrow of our motion is clear, the current is real, the basin exists, but the source of that basin is still partially hidden behind our own galaxy's dust. And that means the story isn't about a single object, it's about a region, a gravitational landscape, and we are sliding across it at 1,000,000 miles per hour. And the direction we are heading is the one place the sky refused to show us. If you draw a full map of the sky and then lay the Milky Way across it, you see the problem instantly. A bright, thick band cuts the map in half. That band is not decoration, it is obstruction. It hides nearly 20% of the observable sky, millions of stars, cold molecular clouds, dense lanes of carbon dust, all of it sitting directly between us and whatever lies beyond. Astronomers gave this region a blunt name, the zone of avoidance, not because nothing is there, because for most of modern history, we avoided looking through it. Point a visible light telescope into that band and galaxies vanish. They don't fade, they disappear. Light from behind the dust simply never makes it to us. So for decades, sky surveys had a missing strip. Galaxy maps looked like someone sliced out a horizontal wound across the universe, and the arrow of our galaxy's motion pointed straight into that wound. We thought maybe it was coincidence, a directional bias, a sampling problem, but then radio telescopes started listening instead of looking. Hydrogen, the most abundant element in the universe, emits radiation at a wavelength of 21 centimeters. It's faint, but it travels through dust almost untouched. So astronomers built massive dishes to catch that signal. One of the most important stood in Australia, the Parkes Observatory. Picture a white dish the size of a football field pivoting slowly under the southern sky. Instead of images, it collected whispers. Each detection was a spike, a galaxy announcing itself through hydrogen gas. Behind the zone of avoidance, the spikes multiplied. The hidden region wasn't empty, it was structured. Galaxy groups emerged, then clusters, and when their redshifts were measured, their velocities a pattern appeared. They weren't randomly distributed behind the Milky Way, they were concentrated. One region, near the constellation Norma, stood out. Norma Cluster, a dense galaxy cluster about 200 million light-years away. Thousands of galaxies packed into a gravitational knot. In visible light, it was nearly invisible behind dust. In radio and infrared, it flared into view. At first, this seemed like the answer. We thought, the Norma cluster is pulling us. Evidence. It sits almost exactly in the direction of our peculiar velocity. Implies. This is the Great Attractor. But when astronomers calculated the mass of the Norma cluster, the numbers came up short. Mass creates gravity. Gravity creates acceleration. Acceleration creates velocity. And the velocity of our galaxy measured precisely against the cosmic microwave background required more mass than Norma alone could provide. So the search widened. Infrared astronomy became the next tool. Unlike visible light, infrared penetrates dust more effectively. Your own body glows in infrared. Remote controls use it. It slips through places visible light cannot. In the 1980s, a satellite called IRIS, the infrared astronomical satellite, scanned the entire sky. For the first time, the zone of avoidance began to thin. Galaxies that optical surveys missed appeared as soft infrared smudges. Later, a deeper survey called 2MASS, the 2-micron all-sky survey, pushed even further. It mapped nearly the entire sky in near-infrared wavelengths. The missing strip shrank. Behind the Milky Way, a large-scale structure emerged. Not just a cluster, a wall. The Centaurus wall is what astronomers now call part of this structure, a filament of galaxies stretching across tens of millions of light-years, threading through the Norma region. Filaments are strands in the cosmic web, the large-scale network of matter that connects clusters across the universe. Imagine a three-dimensional spiderweb. The nodes are clusters, the strands are filaments of dark matter and galaxies. Norma sat at one of those nodes, and the Centaurus wall was one of its strands. Now the picture sharpened. We thought the Great Attractor might be a single, massive object. Evidence? Galaxy flows converged on a region, not a point. Implies. We were dealing with a gravitational basin, not a lone giant. A basin is different from a peak. If you pour water onto uneven ground, it doesn't rush toward a single rock. It flows toward the lowest region, the entire depression. That's what velocity field maps began to show. Using galaxy redshift catalogs and peculiar velocity surveys, astronomers reconstructed the flow of matter in 3 dimensions. They traced where galaxies were moving, not just where they were. The result looked like a watershed map. Lines converging, streams merging, all draining toward a broad region centered near Norma. That region became known formally as the Great Attractor, not because it is the biggest structure in the universe, but because it dominates our local gravitational landscape. Here's where scale matters. The Great Attractor lies roughly 150 to 250 million light-years away. That's far. Light leaving that region began traveling toward us before mammals existed, and yet gravity acts instantly across space. Its influence shapes motion long before light arrives. So, while we see an ancient image of that region, its gravitational effect is present now, and the flow isn't subtle. Our local group, the Milky Way, Andromeda, and dozens of smaller galaxies moves together at roughly 1.3 million miles per hour relative to the CMB. The Virgo cluster, about 54 million light-years away, contributes slightly to that motion, but not enough. The Norma cluster contributes more, but still not enough. When astronomers added up all known masses in the region, something was missing. That missing mass is partly dark matter, invisible, detectable only through gravity. Every galaxy sits inside a dark matter halo, extending far beyond its visible stars. Clusters sit inside even larger halos. The Centaurus wall and Norma cluster are threaded together by these halos, forming a larger dark matter concentration. But even including dark matter, the gravitational pull seemed too broad, which meant the Great Attractor wasn't just Norma. It was an extended region, possibly connected to even larger structures beyond. This is where the emotional weight shifts, because once we mapped enough of the zone of avoidance to see structure, the mystery didn't shrink. It expanded. The more we revealed, the more complex the gravitational landscape became. Picture zooming out on a satellite map of Earth. First you see your city, then your country, then continents. With each zoom, patterns you couldn't see before emerge. That's what happened here. Norma was not alone. Clusters around it formed a supercluster scale concentration, and our galaxy was not outside this structure. We were inside its outer slope, which means our motion is not just toward an external object. It is part of a larger gravitational basin we already belong to. We thought the zone of avoidance hid a single massive culprit. Evidence showed a network. Implies the Great Attractor is a region of converging mass, not a monster in the dark. But even that wasn't the end, because once velocity maps expanded beyond the immediate Norma region, they revealed something even stranger. The gravitational basin extended farther than expected. The flow lines didn't just end at Norma. They continued, like rivers merging into something deeper. And if Norma wasn't enough, what was sitting beyond it? That question marks the boundary between what we mapped and what was still hidden, because the zone of avoidance never fully disappeared. Even with infrared and radio surveys, the densest parts of the Milky Way, especially near the galactic center, remain chaotic and confused. Too many foreground sources, too much dust. About 10% of the sky is still extremely difficult to probe, and the arrow of our galaxy's motion passes close to that opaque region, which means some part of the gravitational story is still buried behind our own stars. We are already moving. We have named part of what pulls us. But the wall behind our galaxy has not given up everything, and what lies beyond Norma may change the scale of the story again. By the late 1980s, the word was everywhere in cosmology circles. The Great Attractor. It sounded dramatic, almost fictional, but the name came from measurements, not imagination. When astronomers mapped the peculiar velocities of elliptical galaxies across hundreds of millions of light years, they found a pattern that could not be ignored. Galaxies weren't just drifting outward with the Hubble flow, they were streaming sideways, like iron filings dragged by a hidden magnet. One research group became famous for this work. They were nicknamed the Seven Samurai. Using galaxy brightness and motion relationships, they estimated distances and velocities independently of redshift alone. What they found was unsettling. The local group was not moving randomly. It was falling toward a region roughly 200 million light-years away in the direction of Centaurus and Norma. We thought the Milky Way was just riding the expansion of space, but evidence showed we were accelerating toward a gravitational basin. That implies a mass concentration enormous enough to bend the motion of thousands of galaxies. Not one galaxy, not one cluster, thousands. At the center of the visible structure sat the Norma cluster, also catalogued as Abell 3627, a massive galaxy cluster buried behind the Milky Way's dust. In X-ray images, it glows from superheated gas at tens of millions of degrees. In radio maps, it crackles with hydrogen emissions. Norma contains thousands of galaxies. Its total mass is equivalent to thousands of Milky Ways. That sounds like enough. But when astronomers modeled the gravitational pull needed to produce our measured peculiar velocity around 1.3 million miles per hour relative to the cosmic microwave background, Norma alone could not account for it. The pull was too wide, too smooth, too distributed. So the idea shifted. We thought the Great Attractor was a single cluster. Evidence showed a larger concentration extending across tens of millions of light-years. That implies a supercluster-scale gravitational basin. This is where the term Laniakea enters the story. In 2014, astronomers mapped galaxy motions across a region spanning roughly 500 million light-years. Instead of focusing only on where galaxies were located, They traced where they were flowing. The technique looked like meteorology, arrows overlaid across space, showing direction and speed, streams merging, boundaries forming. They identified a single massive velocity basin, a region where all matter inside it flows toward a common gravitational center. They named it Laniakea. The word comes from Hawaiian. It means immeasurable heaven. Laniakea is not a cluster. It is not even just a supercluster. It is a gravitational watershed. Inside this basin are about 100,000 galaxies, including the Milky Way, the Virgo cluster, the Norma cluster, all connected through the cosmic web. And at the gravitational heart of Laniakea sits the Great Attractor region. That changes the scale completely. We thought the Great Attractor was something we were heading toward from the outside. Evidence showed we are already inside its larger basin. That implies our galaxy is not an approaching visitor. We are a participant in the flow. Picture standing in a valley during a rainstorm. You are not walking toward the river. You are already on the slope, and gravity is doing the rest. That's Laniakea. Our local group sits near its outer boundary, but the direction of flow is clear, toward Norma, toward the Great Attractor. Velocity maps show galaxies tracing long arcs, like streams bending downhill. The Virgo Supercluster, once thought to be our primary large-scale home, is only a smaller component within this larger basin. Virgo is like a hill inside a much bigger valley, and the valley floor lies near the Great Attractor. But here is where the story twists again, because just when it seemed like the Great Attractor had been properly framed as the center of Laniakea, new data revealed something larger lurking beyond. Behind the Great Attractor, further out in the same general direction, sits an even more massive structure, the Shapley Supercluster. Located roughly 650 million light-years away, Shapley is one of the most massive concentrations of galaxies in the observable universe. It contains more than 30 rich galaxy clusters. At its core sits Abell 3558, a cluster so massive it dominates X-ray maps of that region. If Norma is a city, Shapley is a continent. We thought the Great Attractor was the dominant engine. Evidence showed Shapley has even greater total mass. That implies part of our peculiar velocity may originate beyond the Great Attractor itself. This is where the gravitational picture becomes layered. Norma pulls. The Centaurus wall channels matter into it. But beyond that, Shapley exerts its own influence. Galaxy flow maps reveal that the direction of motion does not stop at Norma. It continues, bending slightly, extending deeper into the southern sky. In simulations of the cosmic web, superclusters form at nodes where dark matter filaments intersect. These filaments stretch hundreds of millions of light-years. The Great Attractor region appears to be one such node, but Shapley sits along the same extended filament. Like two whirlpools connected by an invisible current, dark matter is the scaffolding that makes this possible. Ordinary matter, stars, gas, galaxies accounts for only a small fraction of total mass. The majority resides in dark matter, halos, and filaments. These halos overlap, they merge, they extend beyond visible boundaries. The Great Attractor's visible clusters are just the bright cores of much larger dark structures. Simulations like Illustris TNG model this in detail. Starting from early density fluctuations after the Big Bang, they evolve billions of years forward. The result looks like a cosmic neural network. Dense nodes, thin strands, vast voids. When we overlay observational maps of our region onto these simulations, the match is striking. The Great Attractor region aligns with a massive dark matter node. But simulations also suggest something important. Nodes do not exist in isolation. They connect, and Shapley may be connected to the Great Attractor by a dark matter filament stretching across hundreds of millions of light-years. That means what we call the Great Attractor might not be a final destination. It could be the foreground peak of a larger mass concentration. We thought the story ended at Norma. Evidence showed a deeper structure extending toward Shapley. That implies our motion is influenced by multiple gravitational layers. And that matters, because if Shapley contributes significantly to the overall flow, then the Great Attractor is not the ultimate anchor. It is part of a larger gravitational complex. Velocity reconstructions indicate that Shapley may account for a substantial fraction of our measured peculiar velocity, possibly comparable to the Great Attractor itself, which means the gravitational tug-of-war shaping our galaxy spans at least 650 million light-years. And that still might not be the full story, because even when astronomers include Norma, Centaurus Wall, and Shapley in their models, small discrepancies remain, subtle mismatches between predicted and observed velocities. That's where tension enters. Not danger, not catastrophe, but incomplete accounting. The gravitational math suggests we may not yet have mapped every significant contributor. And remember, the arrow of our motion passes through a region where parts of the sky remain difficult to observe. The zone of avoidance is thinner now, but it is not gone. Behind the densest dust lanes, some structures remain poorly constrained, which raises a possibility. What if the Great Attractor region contains additional mass concentrations we have not fully resolved? Or what if the true center of the gravitational basin is not a single cluster at all? Maybe it is diffuse, distributed, a cloud-like core rather than a point. Imagine trying to find the center of a hurricane while standing inside it. The pressure gradient is clear, the winds are measurable, but pinpointing a single fixed spot is harder than it sounds. The Great Attractor may be similar, a gravitational heart made of many overlapping components rather than one dominant object, and we are already moving within its influence. This is not a story about a monster hiding behind the Milky Way. It is a story about structure, layered structure, a basin inside a supercluster, inside a web, inside a universe that is expanding while gravity organizes it locally. Norma was not enough. Shapley may not be enough either. And that realization pushes the investigation further outward. Because if pull alone cannot fully explain the motion, then something else might be shaping it too. For years, the story sounded simple. A massive region called the Great Attractor was pulling us in. Gravity explained everything. But gravity is never that simple. When astronomers refined their velocity maps using larger galaxy catalogs, something uncomfortable appeared. The direction of our motion didn't point cleanly at Norma. It didn't point cleanly at Shapley either. It pointed somewhere between. A compromised direction. That's a clue. If one structure dominated completely, the vector would align cleanly with it. But our peculiar velocity is tilted, offset, slightly skewed. That suggests competing influences. We thought the Great Attractor was the primary engine. Evidence showed the direction of motion was shared between multiple mass concentrations. That implies the gravitational landscape is multi-centered. Imagine standing between two massive mountains in fog. You feel gravity pulling you downhill, but the slope curves. It doesn't fall straight toward either peak. It bends toward the lower combined valley between them. That's what the velocity field resembles. Norma pulls strongly at shorter range. Shapley pulls across a broader, deeper scale, and both lie in roughly the same quadrant of the sky. But that still doesn't explain everything. Because when astronomers accounted for the gravitational pull of the Great Attractor region and the Shapley Supercluster, some models still predicted slightly less motion than we observe. The discrepancy isn't huge. But in cosmology, small mismatches matter. That led to the idea of bulk flow. Bulk flow describes coherent motion of galaxies across extremely large volumes of space, larger than any single supercluster. Instead of individual basins, entire regions drift together relative to the cosmic microwave background. Some surveys suggested that thousands of galaxies across nearly 1 billion light-years share a slight directional motion toward the same general southern sky region. If true, that implies mass concentrations even farther out may be contributing. We thought Shapley was the far limit of influence. Evidence hinted at motion extending beyond it. That implies something larger may sit deeper in that direction. Now we enter uncertain territory. Bulk flow measurements are debated. Different galaxy samples produce slightly different results. Some find strong, coherent flow, Others find weaker signals consistent with standard cosmology. But the possibility is real enough to investigate. To test it, researchers turned to constrained simulations. Unlike ordinary simulations that start with random initial conditions, constrained simulations use actual observational data from our local universe. They seed the model with measured galaxy positions and velocities, then let gravity evolve the system forward and backward in time. One of the most advanced frameworks for this is the illustrious TNG simulation suite. These simulations model volumes roughly 1 billion light-years across, tracking billions of particles representing dark matter and gas. When constrained to resemble our local cosmic neighborhood, they consistently produce structures similar to the Great Attractor and shapely massive nodes connected by dark matter filaments. But they also reveal something else. These nodes are rarely isolated. They are part of extended complexes. Dark matter filaments stretch like highways between superclusters, channeling matter across hundreds of millions of light-years. If the Great Attractor and Shapley are connected by such a filament, then what we perceive as two separate giants may actually be two peaks within a single extended gravitational ridge. That changes the narrative again. We thought the Great Attractor and Shapley were separate actors pulling independently. Evidence suggests they may be linked components of one larger structure. That implies the attractor may not be a point or even a basin, but part of a vast gravitational superstructure. And here's where scale begins to distort intuition. Shapley sits about 650 million light-years away. Light from that region began traveling toward us before complex life existed on Earth. Yet, its gravitational influence contributes measurably to our galaxy's motion today. Gravity acts across these enormous distances because mass curves space-time continuously. It doesn't wait for light to deliver the news, but distance weakens influence. The farther a mass sits, the less pull it exerts. So if Shapley contributes significantly despite its distance, its mass must be extraordinary, which it is. The Shapley Supercluster contains over 8,000 galaxies in its densest core regions and more than 30 major galaxy clusters. Its total mass exceeds that of the Great Attractor region. In X-ray images, its hot intracluster gas glows across vast swaths of sky. In redshift maps, it appears as a dense wall of galaxies stretching across space. Yet even Shapley may not be the final boundary, because some bulk flow analyses suggest motion patterns that extend beyond 650 million light-years, possibly approaching 1 billion or more. What structure at that distance could influence us? No confirmed supercluster larger than Shapley has been identified in that precise direction, which raises two possibilities. Either the bulk flow signal is a statistical artifact, or our map remains incomplete. And remember, the zone of avoidance still blocks a narrow but critical strip near the galactic center. Even with infrared and radio surveys, the densest molecular clouds create confusion. Foreground stars crowd the field, radio sources overlap. Separating background galaxies from local noise becomes extremely difficult. About 10% of the sky remains stubbornly opaque, and the direction of our peculiar velocity passes close to that opaque strip. We thought modern surveys had eliminated the blind spot. Evidence shows a final band remains difficult to penetrate. That implies additional mass concentrations could still be partially hidden. Now consider another twist. Until this point, the story has focused on pull. Mass attracts, clusters pull, superclusters pull. But what if part of our motion is not driven only by what lies ahead? What if something behind us also plays a role? Velocity maps don't just show flow toward dense regions. They also show flow away from emptiness. Cosmic voids are enormous underdense regions spanning hundreds of millions of light-years. Inside them, galaxy density drops dramatically. In a void, there is less gravitational pull from the inside than from the surrounding walls, so matter flows outward from void interiors toward denser boundaries. This creates an effective push, not a true force, but an imbalance. If a massive void sits opposite the Great Attractor, its underdensity could contribute to our motion by effectively pushing us toward the attractor. We thought our galaxy was only being pulled, evidence suggests we may also be pushed. That implies our motion is the result of a dual-engine system. Pull from the front, push from behind, and that push has a name. But before we get there, step back and feel the scale. You are on a planet orbiting a star. That star orbits the center of the Milky Way at roughly 500,000 miles per hour. The Milky Way itself moves at about 1.3 million miles per hour relative to the cosmic microwave background, and that motion is shaped by structures spanning up to 650 million light-years, possibly more. The gravitational chessboard is enormous. Norma, Centaurus Wall, Laniakea, Shapley, dark matter filaments stretching between them, and still, the direction of our motion is not perfectly accounted for by pull alone, which means the story of the Great Attractor is incomplete, because if you map every visible mass concentration in front of us and still see excess motion, you have to look behind. For decades, we described our motion with one word: pulled. The Great Attractor pulls us, Norma pulls us, Shapley pulls us. It made intuitive sense. Gravity attracts mass. End of story. But when astronomers reconstructed the three-dimensional velocity field of over 8,000 galaxies across hundreds of millions of light-years, the arrows didn't just converge forward, they diverged behind us. That is the moment the narrative split. We thought our galaxy was falling towards something massive ahead. Evidence showed part of our motion is driven by something empty behind. That implies we are not just being pulled, we are being pushed. On the opposite side of the sky from the Great Attractor, in the general direction of Perseus and Pisces, velocity maps revealed a vast underdense region, not just a small gap between clusters, a cosmic void, a region hundreds of millions of light-years across, where galaxy density drops dramatically. Astronomers named it the dipole repeller. The name sounds dramatic, but the physics is simple. In a dense region, gravity pulls inward from all sides. In a void, there is less mass pulling from the inside. The surrounding walls exert a stronger net gravitational influence. Matter inside a void flows outward toward the denser edges. This creates an effective push away from the emptiness. Not a new force, just imbalance. Imagine standing between a massive mountain and a deep valley. The mountain pulls you downhill. The valley, having less mass, pulls you less strongly in its direction. The net result is acceleration toward the mountain. Now scale that to hundreds of millions of light-years. The dipole repeller sits behind us like an enormous gravitational deficit. We thought the CMB dipole was explained entirely by attraction toward the Great Attractor. Evidence showed roughly half of our peculiar velocity may be due to repulsion from the dipole repeller. That implies our galaxy rides a tension between density and emptiness. Velocity reconstructions visualize this clearly. When astronomers trace streamlines of galaxy motion, they see flow lines diverging from the void region and converging toward the Great Attractor basin. It looks like a cosmic wind pattern, air rising from a low-pressure region and sinking into a high-pressure one. The dipole repeller spans a region comparable in scale to the Great Attractor, hundreds of millions of light-years wide. Inside it, galaxies are sparse. Dark matter density is low. The cosmic web thins. At its boundaries, filaments thicken as matter drains outward. We thought voids were passive background features. Evidence shows they actively shape motion on the largest scales. That implies the universe's structure is defined as much by absence as by presence. Now reconsider our velocity. The Milky Way moves at about 1.3 million miles per hour relative to the cosmic microwave background. If you decompose that motion into vector components, roughly half aligns with the gravitational pull toward the Great Attractor region. The other half aligns away from the dipole repeller. Two engines, one in front, one behind, and both are enormous. This dual-engine model solved several inconsistencies. Before accounting for the dipole repeller, predicted velocities from visible mass concentrations were slightly lower than observed values. Add the void's push, and the numbers align more cleanly. We thought missing mass ahead explained the discrepancy. Evidence showed missing mass was not the only explanation. That implies structure behind us matters just as much as structure ahead. But the picture grows even more complex. On the northern side of the sky, opposite the Great Attractor region, lies another major structure, the Perseus-Pisces Supercluster. This is not a void. It is a long, curved filament of galaxy clusters stretching roughly 300 million light-years. At its core sits the Perseus cluster, dominated by the giant elliptical galaxy NGC 1275. Perseus-Pisces exerts its own gravitational pull, partially counteracting the southern attractor's influence. So our motion is not a simple two-body problem. It is a multi-vector solution. Great Attractor pulling from the south, Shapley reinforcing that pull from deeper south. Dipole repeller pushing from the north. Perseus, Pisces, pulling from the opposite side. The net motion is the sum of all these influences. That is why our peculiar velocity does not point precisely at Norma or Shapley. It points somewhere between. We thought cosmic motion was dominated by one giant mass. Evidence shows it is the result of competing large-scale structures. That implies our galaxy's trajectory is a negotiated path through a crowded gravitational landscape. Now, consider what this means for Laniakea. Laniakea is defined as a velocity basin, a region where all matter flows toward a common center. That center lies near the Great Attractor. But beyond Laniakea's boundaries, velocity flows diverge toward other basins. The dipole repeller marks one such boundary. If you map these basins across space, they resemble watersheds on Earth. Rain falling on one side of a mountain flows into one river system. Rain on the other side flows into another. Our local group sits within Laniakea's watershed. The dipole repeller marks a neighboring basin with far less mass. We are already moving inside this watershed. But here is the twist. When cosmologists test these velocity fields against the cosmological principle, the idea that the universe is isotropic and homogeneous at large scales, they find something interesting. On very large scales, the principle holds. The universe averages out to uniformity. But on scales of a few 100 million light-years, strong asymmetries exist. Our region is not average. It is structured. We live near one of the densest and most dynamically complex gravitational environments in the observable universe. That doesn't mean we are special. It means structure clusters. And we happen to be in a cluster of clusters. The dipole repeller also highlights something else. Emptiness grows. As the universe expands, voids expand too. Dark energy accelerates cosmic expansion on the largest scales. That expansion stretches underdense regions faster than dense ones. So, while the Great Attractor basin continues to gather matter locally, the dipole repeller void grows emptier. The tension between gravity and expansion defines the long-term future. Locally, gravity wins. Clusters merge. Galaxies fall inward. The Norma cluster processes incoming galaxies through RAM pressure stripping and mergers. Globally, dark energy wins. Distant galaxies recede faster than gravity can pull them back. Our galaxy is caught between these regimes, pulled by nearby mass, pushed by nearby emptiness, carried outward by cosmic expansion. We thought the Great Attractor was the whole story. Evidence shows it is only one side of a gravitational equation, and that equation balances across nearly 1 billion light-years of space. When you zoom out far enough, the universe looks like a network of tension lines, dense nodes pulling inward, voids expanding outward, filaments channeling matter between them. Our motion is the result of this network, not a single anchor, which means even if we perfectly mapped every galaxy inside the zone of avoidance, we would still need to account for the void behind us and the superclusters beside us. The Great Attractor is powerful, but it does not rule alone. And just when it seemed we had identified the major players Great Attractor, Shapley, Dipole Repeller, Perseus-Pisces, a discovery in 2017 reminded astronomers of something humbling. The map was not finished, because buried deeper behind the Milky Way's dust, farther than the Great Attractor itself, another massive structure had been hiding in plain sight. In 2017, something changed. Not in the sky. In our map of it, astronomers using deep radio surveys of the southern sky detected a concentration of galaxies buried behind the thickest part of the Milky Way's dust. This region had resisted optical surveys. Even infrared struggled there. Foreground stars crowded the view. Dust dimmed the signal, but radio waves passed through. The survey used the 2-1 centimeter hydrogen line, again the same whisper that first exposed hidden galaxies decades earlier. This time, the sensitivity was higher. The sky coverage was broader, the analysis sharper, and what emerged was not a small cluster. It was a supercluster. They named it the Virgo Supercluster. Virgo sits roughly 800 million light-years away, more than 3 times farther than the Norma cluster. It stretches across nearly 300 million light-years of space, thousands of galaxies, multiple rich clusters, filaments connecting them, and it lies in almost the same general direction as the Great Attractor. We thought the Great Attractor and Shapley defined the gravitational landscape in that quadrant. Evidence showed another massive structure hiding between them. That implies the gravitational field in that direction is even more complex than previously modeled. The Virgo Supercluster had gone unnoticed for so long because it sits directly behind one of the densest parts of the zone of avoidance. From Earth, it was concealed by our own galaxy's structure. Its discovery forced astronomers to recalculate local velocity models. If Vela contributes even a small fraction of additional gravitational pull, the net vector of our peculiar velocity shifts. Small shifts matter. Because cosmology relies on precise measurements of motion relative to the cosmic microwave background, deviations can signal new structure. When Vela was added to the models, some discrepancies shrank, but not all, which leads to a deeper realization. We thought our cosmic neighborhood was mostly mapped. Evidence showed that even in the 21st century, entire superclusters can remain hidden. That implies our understanding of local structure may still be incomplete. Now zoom out. We have the Great Attractor region anchored by the Norma cluster about 200 million light-years away. We have the Shapley supercluster around 650 million light-years away. We now have the Vela supercluster roughly 800 million light-years distant, all lying within roughly the same broad southern sky direction. And we have the dipole repeller void in the opposite direction. That is already a massive gravitational network. But there's another piece. Some peculiar velocity surveys have hinted at what is called a bulk flow extending beyond Laniakea, beyond even Shapley. Bulk flow refers to coherent motion across extremely large volumes, possibly approaching 1 billion light-years or more. If confirmed, it would suggest that the gravitational influence shaping our motion extends beyond the structures we have identified so far. We thought adding Vela might close the gap. Evidence suggests there may still be residual flow unaccounted for. That implies either measurement uncertainty or more distant mass concentrations yet to be mapped. Here is where simulations return to center stage. Constrained simulations that incorporate Great Attractor, Shapley, Vela, and known voids produce flow fields broadly consistent with observations. But they also predict something else. Dark matter filaments connecting these superclusters form extended ridges of mass spanning hundreds of millions of light-years. In some models, the Great Attractor and Shapley are connected by a massive dark matter bridge. In others, Vela links into that same network. If true, what we call separate superclusters may be parts of a larger gravitational complex. Imagine standing on a mountain ridge at night. You see peaks rising separately in the darkness, but as dawn breaks, you realize they are connected by continuous high ground. The ridge was always there. You just couldn't see the connections. That is what dark matter filaments do. They bind clusters into larger systems, invisible in optical light. The cosmic web is not decorative language. It is literal structure, and our region of the universe appears to sit along one of its densest strands. But even with Vela included, some bulk flow analyses suggest motion extending toward distances approaching 1 to 3 billion light-years. At those scales, identifying specific mass concentrations becomes difficult. Surveys become sparse, signal-to-noise drops. Could there be a Shapley extension, a broader density enhancement beyond the known boundaries of the Shapley Supercluster? Some researchers have proposed exactly that, not a single giant cluster, but a concentration of multiple clusters forming an extended mass enhancement across enormous scales. We thought Shapley might be the ultimate attractor. Evidence hints that Shapley may itself be part of something larger. That implies the gravitational landscape might not have a single dominant center. Instead, we may be inside overlapping basins, nested within larger basins. At this scale, terminology becomes slippery. What qualifies as a supercluster? Where do its boundaries end? Unlike galaxy clusters, which are gravitationally bound systems, superclusters may not be fully bound. They are regions of enhanced density and shared motion. Over billions of years, some of these structures may merge, others may be pulled apart by dark energy, which brings in the long-term tension. Locally, gravity organizes matter into clusters and superclusters. Globally, dark energy drives accelerated expansion. The further away a structure sits, the more expansion competes with gravitational pull. So even if Shapley and Vela exert influence now, the accelerating expansion may eventually weaken their connection to us. But at present, their gravitational signatures are measurable. The arrow of our peculiar velocity still leans toward that southern quadrant. And here is the subtle but critical point. Each time we thought the map was nearly complete, a deeper layer emerged. First, the zone of avoidance hid Norma. Then, deeper surveys revealed Shapley's dominance. Then, Vela appeared in 2017. Now, bulk flow hints suggest influence may extend even farther. We thought the Great Attractor story was old news. Evidence keeps rewriting the margins. The map is not finished, and it may not just be missing small pieces. It may be missing scale. Because if entire superclusters can remain undetected behind our own galaxy until recently, then the possibility of additional mass concentrations hidden in the remaining opaque strip cannot be dismissed. That strip, roughly 10% of the sky, lies thickest near the galactic center. Foreground radio sources overlap. Infrared confusion increases. Optical light is nearly useless. New instruments are being built specifically to attack this final blind spot. The square-kilometer array will map hydrogen emission with unprecedented sensitivity. The Vera Rubin Observatory will track galaxy positions and motions across vast volumes. X-ray missions like eROSITA map hot gas in clusters, even through moderate dust. Each instrument adds a layer, but none has yet fully penetrated the densest regions, which leaves us with an uncomfortable but honest conclusion. We have identified major structures shaping our motion: Great Attractor, Shapley, Vela, Dipole Repeller, Perseus, Pisces, but there may still be additional contributors, and if there are, they sit either deeper behind the zone of avoidance or farther beyond our current survey limits. We are already moving. We have named the main forces, but the gravitational equation is still being refined. And the next twist is not about something massive ahead. It is about something even more unsettling. What if our entire region of the universe is not average at all? Cosmology begins with an assumption. On the largest scales, the universe is uniform. It has no center, no preferred direction, no special location. This idea is called the cosmological principle. If you zoom out far enough beyond clusters, beyond superclusters, matter should smooth out. The universe should look statistically the same in every direction. That symmetry is called isotropy. For decades, observations supported it. The cosmic microwave background is uniform to 1 part in 100,000. Galaxy surveys averaged across billions of light years show large-scale homogeneity. But our local region? It is not uniform. It is lopsided, dense in one direction, void in another, threaded by massive filaments, anchored by superclusters like Shapley and Vela. We thought these were ordinary fluctuations. Evidence shows our neighborhood may sit in an unusually structured region. That implies we could be living in a statistical outlier, not the center of the universe, but perhaps inside a particularly dense knot of the cosmic web. Zoom out to a scale of a few 100 million light-years, the scale of Laniakea. The density contrasts are enormous. Massive basins of attraction, expansive voids. On those scales, isotropy clearly fails. That's allowed. The cosmological principle applies at much larger scales, but some measurements complicate even that reassurance. One of the most controversial features in the cosmic microwave background is the cold spot. Located in the southern sky in the constellation Eridanus, it spans about 13 degrees across the sky. That is roughly 26 times the apparent width of the Moon. Its temperature is slightly colder than surrounding regions, still within statistical possibility but rare. One proposed explanation is a supervoid along the line of sight, a region of extremely low density stretching perhaps 1 billion light-years. As CMB photons pass through an expanding void, they lose a small amount of energy due to the integrated Sachs-Wolf effect. The void expands while the photon crosses it, stretching the photon's wavelength slightly more than average. The result is a cold imprint. We thought the cold spot might just be statistical noise. Evidence suggests it could reflect large-scale structure. That implies voids of extraordinary size may exist. If true, then the structure of the universe at scales approaching 1 billion light-years may be more uneven than once assumed. Now connect that to our local story. To the south, we have Great Attractor, Shapley, Vela. To the north, we have Dipole Repeller and other large voids. Some analyses suggest that the large-scale flow of matter in our region aligns loosely with these asymmetries. Could our local supercluster be embedded in a broader anisotropic region? Most cosmologists say no. At the largest scales surveyed so far, uniformity holds. But the tension remains interesting, because when velocity surveys measure bulk flow across enormous volumes, the direction often aligns roughly with the southern sky quadrant dominated by Shapley and Vela. Some of these measurements are contested. Different methods yield different magnitudes, but the possibility lingers. We thought our region was cosmologically ordinary. Evidence suggests it is dynamically dramatic. That implies our cosmic address may be more structured than average, at least locally. Now imagine explaining the sky from the perspective of an observer billions of years in the future, after cosmic expansion has pushed distant galaxies beyond visibility. That observer might see only their merged local cluster. No Shapley, no Vela, no dipole repeller, no cold spot. From their vantage point, the universe might look small and isolated. Our era is different. We can still map the cosmic web around us. We can still detect superclusters hundreds of millions of light-years away. But even now, we see limits. The zone of avoidance still blocks part of the map. Surveys have improved dramatically. Infrared, radio, X-ray, but near the galactic center, confusion reigns. Foreground stars crowd the view, gas clouds emit radio noise, X-ray sources overlap. Separating background galaxies from foreground clutter is difficult. Roughly 10% of the sky remains extremely challenging to map fully, and that 10% includes the densest part of the Milky Way. We thought we had pierced the blind spot. Evidence shows the deepest strip remains opaque. That implies additional structures could still be partially hidden. Now consider the psychological effect. For centuries, humanity assumed the Milky Way was the universe. Then we learned it was one galaxy among billions. Then we learned galaxies form clusters, then superclusters, then basins like Laniakea. Each step expanded the scale. The Great Attractor added another layer, a hidden gravitational basin. Shapley and Vela expanded it further. Dipole Repeller revealed that emptiness matters too. Each time we thought the map was nearing completion, a deeper level emerged. The map is not finished, but here is the important nuance. Even if new structures are discovered in that final opaque strip, they are unlikely to overturn the entire cosmological model. They will refine it, add complexity, sharpen vectors, but they will not create a center of the universe. The Great Attractor is not a central point of creation. It is a dense node in a vast web. The cosmological principle survives, yet the local asymmetry remains real. We live in a region where density contrasts are strong, where superclusters align in one broad direction, where voids stretch behind us, where galaxy flows are coherent across hundreds of millions of light years. That is not average quietness. It is dynamic structure. Now imagine overlaying our galaxy's motion as a glowing arrow across a 3D map of the cosmic web. The arrow threads between filaments, leans toward Shapley, angles slightly away from the dipole repeller, bends gently due to Perseus Pisces. It does not point to a throne. It points to a slope. We are already moving, and our path is shaped by structure far beyond anything visible to the naked eye. Which brings us back to the hidden strip, that remaining 10%. If something massive sits there, something we have not yet characterized, it could slightly adjust our understanding of the gravitational basin's center. It could shift boundaries, refine flow lines, but it will not erase the story. It will deepen it, because the universe keeps revealing structure when we improve our instruments. And right now, new instruments are being built precisely to attack that final blind spot. Radio arrays with collecting areas spanning a square kilometer, optical surveys mapping billions of galaxies, X-ray missions charting hot gas in unseen clusters. The final opaque region is shrinking, not dramatically, but steadily, and what lies inside it, whether additional clusters, dark matter concentrations, or merely the continuation of known filaments, will complete this chapter of the map, but it will not end the investigation. Because even if we fully resolve the Great Attractor's core, even if we chart every cluster behind the Milky Way, the larger question remains, what does any of this actually mean for us? There is one last strip of sky that still resists us. It runs along the densest part of the Milky Way. Thick star fields, cold molecular clouds, turbulent gas. The region near Sagittarius, where our galaxy's supermassive black hole sits. In visible light, it is chaos. In infrared, it thins but not completely. In radio, signals overlap. In X-ray, foreground sources glare. Roughly 10% of the sky remains extremely difficult to map cleanly, and the gravitational center of the Great Attractor Basin lies uncomfortably close to that opaque region. We thought modern astronomy had eliminated blind spots. Evidence shows one final curtain still hangs. Behind that curtain, there may be nothing surprising. The continuation of filaments already mapped on either side. Or there may be additional clusters, smaller nodes, dark matter concentrations that slightly refine the gravitational center. The key point is this. The exact center of the Great Attractor is not a single glowing beacon. It is not a giant hypermassive black hole swallowing galaxies. It is not a cosmic drain. It is a gravitational basin, a region where matter density is enhanced across tens of millions of light years. The Norma cluster anchors one part of it. The Centaurus wall threads through it. Shapley looms farther beyond. Vela extends the structure deeper, and dark matter halos connect them in three-dimensional space. The center of this basin may not be a point at all. It may be diffuse, like trying to identify the lowest exact spot in a valley floor covered in fog. You can measure the slope, you can trace the flow, but pinpointing a single coordinate is difficult. Radio surveys have identified candidate clusters near the densest obscured strip objects catalogued by radio brightness, some lacking precise optical counterparts due to dust. X-ray observations hint at hot gas concentrations. Infrared maps reveal partial structures, but full three-dimensional confirmation requires deeper data. New telescopes are coming online to do exactly that. The square kilometer array will map hydrogen emission across enormous volumes with sensitivity far beyond previous surveys. The Vera Rubin Observatory will repeatedly scan the southern sky, measuring galaxy positions and subtle motions. Future X-ray missions will trace the hot gas that marks massive clusters even when optical light fails. Each new instrument adds clarity, but here is the subtle twist. Even if we fully resolve every structure in that final 10%. Even if we identify every cluster contributing to the Great Attractor Basin, the ultimate nature of the attractor remains unchanged. It is not a single object. It is structure emerging from the cosmic web, and that web is shaped primarily by dark matter. Dark matter makes up roughly 5 times more mass than ordinary matter. It does not emit light. It does not reflect light. It reveals itself only through gravity. Simulations show that dark matter forms long filaments, connecting clusters like threads in a vast network. Galaxies sit at intersections of these threads. The Great Attractor region is one of those intersections. When you remove the visible galaxies from a simulation and look only at dark matter density, the web becomes clearer. Dense nodes, thin strands, vast voids. The Milky Way sits along one strand inside Laniakea. The Great Attractor marks a deeper node along that strand. Shapley marks an even larger node farther along. The dipole repeller marks a thinning of the web behind us. This is not a story of a single gravitational villain. It is a story of topology, of geometry on scales so large that even light takes hundreds of millions of years to cross them. Now zoom in to the Norma cluster. Inside it, galaxies collide. Ram pressure stripping tears gas from spirals like tails behind comets. Supermassive black holes merge. Clusters are not quiet. They process galaxies. They transform blue, star-forming spirals into red, elliptical remnants. The Great Attractor Basin is not only pulling matter inward, it is reshaping it. The jellyfish galaxy ESO, 137 to 1-inch Norma, leaves a luminous tail of stripped gas, stretching over 200,000 light-years, nearly twice the diameter of the Milky Way. That transformation is happening right now. But on timescales of billions of years, nothing in this story threatens Earth. The Great Attractor is about 200 million light-years away. Even at 1.3 million miles per hour, our galaxy would take longer than the current age of the universe to reach that distance. And the universe is expanding. Dark energy accelerates expansion on large scales. Eventually, distant superclusters may recede beyond gravitational reach, which raises the final tension. Gravity pulls locally. Dark energy stretches globally. Will Laniakea eventually collapse inward toward its gravitational heart? Or will expansion isolate its members before they fully merge? Current models suggest that structures already gravitationally bound will remain bound. The local group will merge with Andromeda in about 4 billion years. Virgo will remain part of the basin, but whether Laniakea as a whole will fully collapse into one megastructure depends on the balance between gravity and accelerated expansion. That answer is not fully settled. The Great Attractor may never be reached. Instead, it may remain a region toward which we flow asymptotically, forever moving, never arriving, as expansion stretches the space between large-scale nodes. Which brings us to the quiet realization at the core of this story. We are not stationary. We are not drifting randomly. We are embedded in a dynamic, structured, cosmic flow shaped by invisible mass and vast emptiness. We are already moving, and we have been for billions of years. When early astronomers first mapped the zone of avoidance, they assumed it was an observational inconvenience, a blind spot. Now we understand it as a frontier. Behind that strip lies one of the most gravitationally rich regions of our cosmic neighborhood. It took radio astronomy, infrared surveys, X-ray mapping, and decades of velocity reconstruction to reveal even part of it. And still, the final 10% remains partially unresolved. The map is not finished, but the pattern is clear. The Great Attractor is not a monster. It is a basin in the cosmic web. Its pull is real. Its scale is immense. And our galaxy is one thread among many flowing toward it. The universe does not revolve around us. It does not wait for us. It does not arrange itself for clarity. It forms structure, and we measure it, piece by piece, survey by survey. The hidden region behind the Milky Way is no longer completely hidden, but it is not fully revealed either. And that tension between what we have mapped and what remains obscured is what keeps the investigation alive. Because the deeper truth is this: we have drawn the coastline of our cosmic continent, but we have not finished charting its interior. What this actually means. Step back from the clusters, from the velocity maps, from the names Norma, Shapley, Vela, Dipole, Repeller. Strip it down to the simplest fact. Our galaxy is not floating in empty space. It is part of a flow. For most of human history, we imagined the sky as a backdrop, fixed stars, a stable dome. Even after we learned about galaxies and expansion, we still pictured ourselves as observers standing still while the universe stretched around us. That picture is wrong. We are inside a moving system, shaped by forces spanning hundreds of millions of light years. And that leads to the first real takeaway. First, we do not live at a point. We live on a slope. The Great Attractor is not a destination we will one day arrive at. It is a gradient in space-time, a downhill direction in the cosmic web. You do not feel gravity when you stand on Earth because everything around you accelerates together. The same is true here. The Milky Way, Andromeda, Virgo, all of Laniakea are sliding along a vast gravitational contour. We are already moving. That sentence sounds simple, but it changes perspective. We are not isolated. We are not stationary. We are embedded in structure so large that even light struggles to communicate its scale to us. Every atom in your body is riding that current, not toward destruction, not toward doom, just toward structure. Second, the universe is shaped as much by emptiness as by matter. We tend to focus on what is massive: clusters, superclusters, nodes in the cosmic web. But the dipole repeller teaches something equally important. Voids matter. Emptiness has consequence. In a universe where gravity curves space-time, the absence of mass is not neutral. It redirects motion. It creates imbalance. It defines flow lines just as clearly as dense regions do. The cosmic web is not only a network of bright knots. It is a tension between density and absence, between attractors and repellers. That balance shapes the path of entire galaxies, and it tells us something profound about how structure forms. The universe did not assemble around a central point. It grew from tiny fluctuations. Some regions became slightly denser, others slightly emptier. Over billions of years, gravity amplified those differences. Dense regions pulled in more matter, voids drained, and the web emerged. The Great Attractor is not a special exception to cosmic rules. It is the natural result of those early fluctuations evolving under gravity, which leads to the third takeaway. Third, our maps are temporary. For decades, the zone of avoidance was just a blank strip. Then Norma appeared, then Shapley, then Vela, then velocity reconstructions revealed Laniakea, then the dipole repeller. Each generation thought it had nearly completed the map. Each generation was wrong. The map is not finished, not because we are ignorant, but because the universe is layered. Every improvement in sensitivity peels back another level. Radio revealed what optical could not. Infrared revealed what dust concealed. Velocity mapping revealed what static images hid. Simulations revealed invisible dark matter scaffolding, connecting it all. And still, 10% of the sky remains difficult to probe fully. This is not failure. It is the normal state of science. We draw boundaries around what we know. Then better instruments erase those boundaries. The Great Attractor was once described as mysterious and ominous. Now it is understood as a gravitational basin within Laniakea. One day, its exact mass distribution will be mapped in detail. And when that happens, the story will not end. It will expand, because beyond every mapped structure lies a larger context. Now zoom out one last time. The Milky Way orbits its center at roughly 500,000 miles per hour. The Milky Way itself moves relative to the cosmic microwave background at about 1.3 million miles per hour. Laniakea flows toward a gravitational basin hundreds of millions of light years away. Beyond that, dark energy stretches the universe, accelerating distant galaxies away from us. Locally, gravity organizes. Globally, expansion wins, and we exist at the boundary between those regimes. Nothing in this story threatens Earth. Nothing here changes tomorrow. But perspective shifts. When you look at the night sky now, you are not looking at a fixed canopy. You are looking at a moving landscape. The stars above you are carried by a galaxy sliding through a gravitational valley. That valley is shaped by structures we only recently learned to see. The Great Attractor is not a cosmic monster. It is a reminder that the universe is structured on scales far beyond instinct. A reminder that we discovered that structure not by sight alone, but by motion. By measuring tiny temperature shifts in ancient radiation, by tracing the redshifts of distant galaxies, by listening to hydrogen whispers through radio dishes the size of buildings. The story of the Great Attractor is not about fear. It is about orientation. We now know which way our galaxy is leaning. We know the broad direction of our cosmic slope. We know the names of the major structures shaping it. And we know that our position in the universe is not privileged, not central, not fixed. We are one thread in a web that stretches across billions of light years. And that web continues to evolve. The final blind spot in the sky will shrink. New surveys will refine the flow lines. Future astronomers will redraw the basin boundaries of Laniakea with greater precision. And somewhere, deeper in the web, new structures will come into focus. But the core truth will remain. We are already moving, not alone, not randomly, but as part of something vast, structured, and still unfolding. The universe does not wait for us to understand it. It just keeps moving,